So we're going to find many solutions. That's why we're going to find modes. The thickness is a spatial parameter of the model. It's the thickness of the layer. And the material parameters, beta 1, beta 2, mu 1, mu 2. In some ways, it's similar to what we have found for the plate. But for the plate, omega and k were related with something different.
So, is the video on?
Yes.
Yeah. Yeah. For the plate, we found a plot like this. Or if you want, in the other representation, you can put here omega or f. It's a 2 pi difference. We found something like that. That was the plate. Tangent was there, but here we didn't add this how to say, right term, because we had n pi. I mean, the argument should be n pi, or if you want to play with boundary conditions, free and rigid, something like that, n pi over 2. That was the plate. And this is the new equation that we found for a low velocity layer over Hall space. Please do remember that the condition is this. Beta 1 has to be less than beta 2, otherwise the energy cannot be trapped in the layer. It's going down for Snell's law. And the solutions that we're looking at, and these are called eigenvalues, have to be also less than beta 2. Otherwise, energy is going to go down into the Hall space, critical angle. Okay, so as you can imagine here, we can imagine that this is beta 1, and now we have a beta 2. So we are truncating this. And this is going on. That's the modification compared to the plate. Please do remember that we are dealing with these models, very simple ones, because we want to apply them to the real Earth. So why the plate? Well, because we have a core metal boundary. So we can imagine that a plate, if you deform it and you create a spherical plate, it's going to be useful. That model is going to be useful for what we're going to call torsional modes in the next, after the mini break that we're going to have. While this model here is very useful if you consider flat models. Let's say 1 kilometer, 10 kilometers, 1 kilometer, 1,000 kilometers. Not more, because otherwise the sphericity of the Earth is becoming important. So, good for local and regional models. What else? Once we find the solutions to this problem here, and we will have many, because according to the behavior of a tangent, modes are entering into the game. What else? We can go back using the C's that are satisfying this solution here and look for the eigenvectors, so the displacement versus depth, or better, since we have just one component of the displacement, eigenfunctions. And as we have seen, this equation here cannot be solved analytically in a strict sense, but it can be solved graphically or numerically. And the solutions that we can find are like these ones. Please remember that this is different to the plate, because we cannot have these ones. Why? Because if you remember during the plate, C going to infinite horizontal apparent velocity means that we have a normal incidence and we are bouncing together. We cannot, because for normal incidence in a low velocity layer over Hall space, every time that the wave is bouncing down, part of the energy is going in the Hall space. So after some bounces, energy is lost. So we have to go beyond the critical angle. And that's why we have these cutoffs here. Okay? So these solutions exist because we are looking for this, less than beta 2, more than beta 1. Okay? So to sum up, we have omega and C, dispersion, we have modes, and we can label the modes using their eigenfunctions. So after solving this, and this was an example of a graphical solution, if you remember, I've shown to you the animation when more branches on the tangent were entering inside the computational box that is decided by the values that you put here. Okay, we can imagine now eigenfunctions. This is a very important plot, because please give a look to them. Remember, this is the UY component of displacement, so it's something that is moving. If that is x, is moving like that. It's pure shear. This is the boundary with the Hall space, and you see that here you have an exponential decay, while in the layer it's a combination of sines and cosines. The fundamental mode has no zeros. The first higher mode has 1, the second 2, and so on. Okay, what is important to remember here is modal dispersion. So look, different modes have different values of the velocity. Give a look to this plot here. Look at the fundamental mode at this period, 10 seconds. It's a very important period for seismology, like 1 second, for example. Give a look to the wavelength. Let's say that a 10 seconds wavelength is about 40 kilometers. 40 kilometers is comparable to the thickness of the first layer, that is, in this model here, the crust. So it's filling it. If you give a look to the solution of the first higher mode, velocity is higher. Why? Because it's filling downstairs. It's filling the Hall space more, and the Hall space is faster. So actually this, and you see here the plot, it's going deeper. So actually, if you want to understand this phenomenon of dispersion, in this case here, you can imagine that dispersion is related to the fact that different modes and different frequencies are filling different parts of the structure. Deeper, faster. But if you go to the surface, it's slower. Actually, if you go to higher frequencies, or shorter periods here, 5 seconds, the velocity of the fundamental is getting lower, wavelength is smaller, it's going to be trapped in the layer, while the other ones are filling more of the Hall space. So it's dispersion due to the fact that different modes and each mode at different frequency is filling different parts of the structure. Okay? So that's the summary for lab waves. But we have to remember one thing, that if we have a dispersion, the C, that is the solution here, the eigenvalue from a mathematical point of view, from the physical point of view is a phase velocity. And if we have dispersion, we have to take care about phase velocity and group velocity. Now let me make a step backward to a couple of slides that were in the previous lecture. This morning, early morning, the system was down. I've not tried in the last hour. Any news?
No.
Very good. Okay, so in lecture number, it is this lecture, that is number 10, when I was speaking in general about dispersion, there was this plot here. And these two slides, 3 with the general treatment, are important for any kind of wave that is dispersed. Any. Could be light, could be lab waves, Rayleigh waves, could be gravity waves in fluids. Every time that we have dispersion, we have to take care about different velocities and different frequencies. For example, let's consider again what we studied for beats. If you remember, we considered beats long time ago, 2 different frequencies. At that time, we wanted to study the effect of different sounds with different frequencies arriving at a given point where we were listening, okay? But now, let's try to follow them in space. And now, the system is giving dispersion. What does it mean? That if you take omega 1 and omega 2, the two velocities now will be different. They're not the same. So it's not like for sound waves. Sound wave velocity pretty much is not dispersed. Otherwise, you can imagine it would be a mess. Let's imagine that when you speak, shorter tones and longer tones are arriving at different times. No one could understand each other because some part of the message would arrive later, so something like that. So in principle, in a basic principle, sound waves are not dispersed. But if they are, we will have a strange phenomenon here. Omega 1, omega 2, K1 and K2. But now wait a second. We have not the same velocity. What does it mean? That if we play the game very similar to what we did for bits, in time and space, what we get here using the superposition principle is this. And it is similar. But now we're following the wave trains in space. We're not fixed in space. What's going to happen here? Well, that we will have a phase that is traveling with omega over k, and that's c. And the envelope, so the maximum, the energy, remember that energy is connected to the amplitude, not with the single phase, would travel with delta omega over delta k. But if you reproduce this for a wave packet, it will become d omega over dk. Now, when they are the same, nice, velocities are the same. When they are the same, when omega over k is equal to d omega over dk, line. When we have a line omega k, that's the same. But when we depart from a linear relation there, the slope in a point of a curve and omega over k, they are different. What's happening there? Well, that if you follow zeros and maxima, the slope here will be different from the slope of a single phase, dispersion. So if you want, a nonlinear relation between omega and k are giving dispersion, that is giving Cn group velocity, and vice versa. No dispersion, all the velocities will condense just in one. Let me show to you an animation that is valid for, let's give a look to this. This is a wave packet, okay? Actually, it's very similar to the algebra that we have done here, but for a group. If you do it for a group, you will get this definition with d omega over dk. Good. Now, if no dispersion, all the components of a wave packet will travel together. No dispersion. But if there is dispersion, this is what can happen. Let me start again. Look here. Longer periods here are traveling faster. Shorter periods are slower. What is the result? The wave packet is stretched. In optics, but also in seismology, but the word is coming from optics, we speak about normal dispersion. What is normal dispersion? When longer periods are traveling faster than shorter. Now, let's give a look to this plot here. Longer periods means smaller frequencies. And as you can see here, this velocity is larger than this one. This velocity is larger than this one. It's normal dispersion. Why? Because longer periods, shorter frequencies, are filling the deepest part of a structure that is faster. So they're traveling faster. Shorter periods, the eigenfunction is going to be trapped in the layer that is lower. That's dispersion. So in seismology, we have dispersion that can be labeled with normal dispersion, like in this animation here. But you see how the wave packet is stretched, and now, if you follow the maximum, and you take a clock, and you measure, you will get group velocity. If you follow a single phase here, it's traveling faster. And you can demonstrate that anytime that you have normal dispersion, group velocity is less than phase velocity. If you want to have a proof, it's here. It was the last slide that I was not discussing with you coming from the old lecture. Now what about group velocity? In general, its definition is the omega over dk. Now if you write omega in terms of c and in wavelength, you get this. This in optics is index of refraction. That's why everything, all the terminology is coming from optics. Sorry for that. But if you rewrite it, there you go with a universal definition. Now let's give a look. Group velocity is phase velocity minus wavelength times the derivative of velocity respect to wavelength. If this is, one second, if this is negative, this will be plus and that will be large. If this is positive, that will be minus and this will be smaller. Now, what does it mean? Less than 0, this. Velocity is decreasing with, positive means velocity is increasing with wavelength, like in that case here. Yes?
For normal dispersion, we know that there is the connection between refractive index mu and lambda is suggested by the Cauchy. And
now, wait a second. You're right, but I was using this terminology here with n only because the original term is coming from optics. Now, in seismology, we don't have n. We don't have a standard velocity, because in vacuum, we have no seismic waves. That's why I was using this, and you have an expression in optics, but I prefer this, because for seismology, that is what we need to use. We don't have n. Speed of light in vacuum is a standard.
but there is the connection between mu and speed, or n and speed.
If you want, that is intrinsic dispersion. So index of refraction is a sort of a constitutive law of a material respect to the speed of light in itself. Now, let's take our model, a layer over a half space. Now here we have beta 1. Beta 1 is not. Mu here is modulus of rigidity. There is no frequency. This velocity is the same for all the frequencies. If you take beta 2, we have no frequency. So actually, the two materials overposed are not dispersing anything. But the system, as a layer over half space, when beta 1 is less than beta 2, is creating a dispersion that is different. It's called waveguide dispersion. Why? Because energy is trapped here. It can be described by modes, and those modes are dispersed because we are feeling different parts of a structure at different frequencies. So we don't have an index of refraction because actually the velocities are not dispersing. That's why the second expression there is important. But this panel here is actually valid only for optics. We don't have n. In the second term, we're going to speak about anelasticity. Anelasticity will add a little bit of powder of intrinsic dispersion inside materials. So if you take a perfect elastic material like this, you don't have dispersion. But if you add a little bit of anelasticity, it's going to show a weak fashion of dispersion. But not now.
But still we are using the normal dispersion. If that-
Just the name. It's like me, I'm Fabio, like Romans 2000 years ago. Okay, but I'm a different. The name is the same. Normal is whenever this derivative is positive. This derivative. So velocity respect to wavelength. So this is coming from optics. This is a general definition. If you want a better vision, it's something like that. In general, I prefer it. Now, omega k plane. If no dispersion, sorry, it's supposed to be a line, omega over k and the omega over the k, they are the same, right? Now, if you take a curve like that, now omega over k and d omega over dk, now they are different. And you see that this is going to be like that, while if you take a curve like that, this is larger. So normal dispersion in the omega k plane means a curve that has a convexity towards down. Not like that. So I don't care, and I'm sorry for that, about n. Okay, let's go back to what we have to do. So here we discussed the 3 slides about general dispersion, very simple, that I forgot to mention during the +-1 lecture. And here you have a beautiful plot of C and U for lab waves for that model. The plot is coming from your textbook. So you see that we have a curve for the fundamental mode of C, and you see that we have a groove velocity that is lower than C and has that shape. They are different. Now, no dispersion, C and U are the same, and actually we couldn't speak about modes. If you put there beta 1 equal to beta 2, nothing is coming out. We have just an SH reflect. If beta 1 is less than beta 2, multiple SHs reflected can interfere and build a lab wave. Before, and here you see the same expression in terms of normal dispersion. And that's why here I was adding this plot here. That is a sort of a recap about what we did. I like it. It's really a recap. Now, what about this? Well, T and X. T and X. Yeah, I know it's Monday. T and X, we call that travel times.
Travel time.
And if you remember, direct, refracted, and then be reflected. Now, in T and X, what is a phase, what is a group? At that time, we were not speaking about phase and group. We didn't care. We just wanted to bookkeep the phases and their variables with clocks, body wave tomography. But if you want, there is a way to distinguish between them, because one is related to single phases, the other is related to energy, right? Now, what about these plots here? Make me happy. Do you remember the ray parameter?
Yes.
And we found that in flat geometry it was dt over dx. So actually, ray parameter, do you remember it? It was related to horizontal apparent velocity. But now is phase velocity. So actually, in this plane here, phase velocity is related to the derivative of the travel time, ray parameter. While groove velocity is related to something that is arriving with energy. If you want, is t x over t 1 over. Now let's go in the omega k plane. In the omega k plane, we were used to study lines. But now we have a different version. In the omega k plane, we have beta 1, beta 2, and the modes that are starting from beta 2 going to beta 1. Now, wait a second. Let's give a look now to phase and groove velocity. Phase is omega over k, but groove velocity is the slope of a curve. Now, look at this one. It's starting with C2. Now, follow the derivative. No, it's too high. Let's imagine to follow here the derivative of this curve. C2, now it's diminishing. It's going to a minimum, then increasing again. Follow this and imagine the slope. Okay? Beta 2, slowing, minimum, increasing again. That's groove velocity. That's why groove velocity is starting with this value, decreasing, getting a minimum, going back to that value. Now, and that's the final but very important message of this first part of the lecture. What's happening here? Let's imagine what's happening when we have a minimum with groove velocity.
No transference of energy.
Yes. Why? Because here, all these periods will arrive with pretty much the same velocity in terms of energy. So you will have a very robust packet arriving there. While here, when the slope is large, this period will be faster than this period, than this period, this period. Wow, here we're going to trap the energy there. That trapping, it's not a trapping, but that accumulation of energy is called Airy phase. That's why every time that you have this plot here with a minimum ground velocity, you may have an Airy phase. It is something that is quite evident in the time domain, because you have a large packet. You see, very simple model, but some basic principles. Now, to really conclude this part, let's relax with an animation. It's not easy to find, just if I'm producing thousands of signals with love waves, it's not easy to find an animation. Let's be static version. Now the family is complete. We started a long time ago with P waves. Then we consider S waves. You do remember that here the divergence of U is 0. Pure shear is going to be transmitted. Here the divergence of U is not 0. Compressions are rarefactions. Changing volume, but not in shape. Changing volume with squeezing, it's like the sound waves. Here, no change in volume. Then we found, just with a free surface, the possibility of having Rayleigh waves. And if you have no layering in the Hall space, they are traveling with no dispersion, with a velocity that is a little bit less than S wave, 92%. But if we add a layer, a low velocity layer, now we can find love waves, dispersion, and Rayleigh waves will be dispersed. Now, what about Rayleigh waves? Yes, the bad news are that we should go back here and write the same formulas for Ux, Uz, sigma Zz, sigma Zx. We have to apply the two, doubling the boundary conditions, free surface, continuity, and damping in the Hall space. Everything is doubled, and we're not going to do that. But please remember that once you have layering with low velocity layers, you have love and Rayleigh waves, both, and dispersion. This is what we have to remember. Now, dealing with love waves, we can, I hope it's still on, give a look to this animation. It's for the fundamental mode. Remember, they are SH, pure SH. So UI, that's X, UI. Amplitude is usually larger in the layer, because in the Hall space it's going to be damped. And here they are. That's fundamental mode with a given frequency. I've not found animation. No, that's not important. Okay, something like that. So please do remember modes and dispersion. The modes can be labeled with fundamental, first higher, second higher. They are not harmonics. Sorry about that. Now, why we are dealing with that? For many reasons. And here you see the most important ones. Because now if you give a look to a real seismic signal, now you can see that there are many important things here. Well, the first arrivals, we know they should be related with P waves. They are faster. Then we have all the possible other phases that are propagating. Because every interface will give birth to other phases with conversions, PSV, SV to P, many of them. Many reflections, many refractions, and in a spherical world, a lot. We have seen them with travel times. Now look, after these phases, the huge wave train related to Rayleigh waves and love waves. Now, look, dispersion. Longer periods are arriving first than shorter periods. The same for Rayleigh, they're a little bit slower. Why? Now we will treat only one model with Rayleigh waves, that is the simplest one. But you have to remember that in the case of a layer, of a Hall space, Rayleigh wave velocity was lower than S. So they are a little bit slower, as you can see here, compared to Lat waves and dispersion. Now why they are large compared to the phases? Because they are cylindrical waves. Because once they are created into the layer, they are traveling like that, cylindrical waves. So they decay as 1 over the square root of distance, and not as 1 over the distance like the spherical wavefronts. That's why they are large. Can we use them to do tomography? Yes, this is what we will see just in a few slides, in a minute. But first, let me show to you a beautiful and the simplest dispersion relation for Rayleigh waves. How to do that? Oh, as I told you, we have to double everything to solve for the boundary conditions and so on. Wait a second. There is a model that is eliminating part of the algebra. Which one? And it is very interesting. It's another one that we have studied. Let's imagine to have a water layer over a Hall space. Now, in the Hall space, we have alpha and beta. Good. But in the water, we have just alpha water. What does it mean? We have no S waves there. But we have P waves, and you can call them sound waves. So actually, if you do the algebra for this model, what we have to do is to apply the free surface condition. Free surface. For water, it's pressure. It's easy. It's only one component, sigma zz. For a liquid, please do remember that the stress tensor is symmetric and just diagonal, and all the terms are the same. It's pressure. Right? Okay. Then what we have to write in the first layer is just a sound wave, just P. Okay? Then what we have to write, oh, sorry for that. I have to rewrite it, but I think it did. What we have to apply here is the continuity of some displacement component. Which one? The vertical for sure. Horizontal, not necessary, unless you take care that this fluid could be viscous. So algebra is much simpler than this. Stress here has to be continuous. pressure here has to be equal to sigma zz. Fine. You see, many components of the algebraic structure are gamma. Then here we can write P and S potential, and we have to apply a damping pair. Otherwise, we are not trapping. If you perform with this and you shake, this is what's coming out. There is a times here. Let's see if I have a version with a better vision. While I'm searching it, please tell me which are the two good old friends that we can find here. I leave it here while I'm opening another one. There are two good old friends. Now you can see. Could be here. So you have 1 minute. Could be here. It's supposed to be. Yes, that's better. And here there is a times. Tell me, please, make a salute to two good old friends. Which one, pardon?
This one?
I put them in 2 lines, just for you to recognize them. Let's give a look to this one. What if could be equal to 0? Let's imagine this is 0. Then that means that that has to be equal to 0, right? How this could be 0? Well, let's imagine that we are switching h, the thickness of a liquid layer, to 0. Or we could say, let's go to so large wavelengths that the 4 kilometers of the ocean are not felt. If it is not felt, we have a null space. Null space means Rayleigh waves. Actually, when this is equal to 0, you're getting back the good old friend of Rayleigh waves in a null space. It's that one, the cubic. Now let's imagine that that part is not important. Have you seen something similar to this one, to the first one? Here. It has the same structure. H, omega, beta 1c, beta 2c. Alpha in the water, alpha. Actually, it is very similar to the sound interference in a low velocity layer over half space. It's like log waves, but just for P. It's an acoustic waveguide. But if you put the things together, you have PSV in a liquid layer over half space. P and PSV. Downstairs, you can go back to the old Rayleigh waves problem. Upstairs, with the half space, you can have a sound velocity waveguide. Just to show to you that we could do the same for Rayleigh waves, for a solid layer over half space, but everything is double. So more complicated than this one. To sum up, let's go to the conclusion. No, these are the hidden slides, sorry. What is really important about this is this. And these are the final slides. Now, please do remember, for seismic body waves, we can essentially trace them in the time domain. Propagation, wavefronts, conversions, arrivals at a given receiver. And we measure the arrival time, Tx, okay, for the different phases. We have seen an example of that bookkeeping, and we've seen the application of them as a starting of body wave tomography. Morovicic, the Moho, at a larger scale, core mantle boundary, inner core, and so on. For surface waves, and they are cylindrical waves, whose amplitude is larger on average at the surface, time is not important, dispersion is important. Because if you go back to that signal, you will understand that here, it's not easy to measure the single phases, but the dispersion, yes. So actually, surface waves are used to do a tomography inversion, but using their dispersive properties, because the dispersion will depend by the velocity that they fill versus depth. Different profiles will result in different dispersions. How to measure dispersion? Well, technically, we have many solutions with many beautiful codes, but the idea is this. You take a signal, you see on the top a very real signal, recorded at, as far as I remember, the complete caption is on the textbook, but it is after some thousands of kilometers, and you give a look to this. You see how it's beautifully dispersed. You take the signal, you go to the frequency domain, and you consider different frequency bands. You make it in slices. For example, here you're filtering 14.5, 19, 28, 51 long periods. If you take the same signals and you consider frequency slices, you see different arrivals. Look at the long periods and the short periods. Now, if you know the distance, you can measure the dispersion, because the maximum arrival, that will be group velocity. So you see, this corresponds to a group velocity of 4.5, while this one corresponds to a group velocity of 3.5. So you take signal, you study its dispersion using the frequency domain and the time domain, and you can measure group velocity. Using that, you can map the interior of the Earth, not using time information, but dispersion information. That is the second important message that I want to leave to you. And if you go at a global scale, this is a beautiful picture that you can get. And it's a sort of a summary for surface waves. Now let's give a look. Let's go here, or here, 100 seconds. Now, 100 seconds corresponds to wavelengths that are roughly, let's use 400 kilometers. So let's say that the penetration depth of the surface waves is 400 kilometers. Now at those depths, lateral heterogeneities are not that strong. That's why Rayleigh and Waves curves are, the same. Now let's go to shorter periods, for example 10 seconds. Now the wavelength is becoming 40 kilometers, 30, 40. What does it mean? That now the waves are filling the crust. And the oceanic crust and the continental crust are very different. And you will have different branches, as you can see here. Now if you go to shorter periods, let's say, as a paradox, 1, now the wavelength is 4 kilometers. Now you're filling really the surface of the Earth. And you can go to shorter periods. So the message here is that these maps, these dispersion curves, can start an inverse problem for tomography. Can you tell me why Rayleigh oceanic is going so low? That's the lowest curve, right? Look at the label. This is called oceanic. What does it mean? Is that we have water in the path. So actually, when you go to short periods, the Rayleigh waves are trapped into the oceanic part. And that means that we have 1.5 wave speed. Angular velocity can be lower. Actually, we are filling water. While love waves are not so low on average, because they cannot propagate in water. It's a SH, right? So for them, the bottom of the ocean is the free surface. Is it? Let's imagine to have this profile here. Water, 4 kilometers, and hull space. That could be layered, whatever. PSV are filling this with the P part of the wave tray. SH, they don't fill this. That's a free surface. They cannot propagate in water. The boundary condition at the ocean bottom for love waves, it's a free surface. Water is like nothing. Ideal water. Are you following me?
Yes.
Okay. So that's why these dispersion curves and their, how to say, variations can be used to study the interior of the Earth. And just as an example, this picture is coming from your textbook, to see how we have a source, we have two receivers that are staying in different parts with respect to the mountain chain, that ridge. And if you give a look, the same source, same periods, but the dispersion curves are different. And this can be used to start an inversion process and to look for the interior of the Earth in, let's say, 150 kilometers. So, as a final recap before a, let's say, 10 minutes break, let's remember that we studied seismic body waves, P and S. S then became SV and SH, according to the free surface. You do remember this. PSV can be coupled at any interface with conversions. P can become S can become P, but only P and SV. SH were separated. Okay, then we followed the travel times of these possible arrivals. And we found the important interfaces inside the Earth. Free surface, the crust, other, maybe a little bit tinier variations, core mantle boundary, inner core. Then we study interference, P and SV, Rayleigh, SH with itself, love. Layered structure, dispersion. From travel times to dispersion curves. They both can be used as a starting point to do tomography. Okay? Travel times, dispersion. These are the key words. Now, what we're going to do after 10 minutes is to give a look to these surface waves as a possible progressive waves e2 ikx minus omega t that can interfere on a global Earth. And they can excite the free modes of the Earth. Love waves will become the torsional as a nickname. Rayleigh waves will become spheroidal. Let me tell you one thing. We could take a whole course on the free modes of the Earth of more than 12 hours. We cannot do that. There is involved a lot of algebra. Why? Because we have to use spherical geometry. So we will go very fast in this. Please, what I want from you is just to remember the physics. And the physics can go back to the good old time of a string. I will skip the 2D modes. I hope you do remember this slide here. That was a string. And we found, thanks to Fourier, and to the completeness of differential operators, that we can write whatever in a string, properly summing the modes, its modes. The modes were decided by eigenfrequencies and eigenvalues, eigenfrequencies, and eigenfunctions. The source was playing the guitar, and we played that, if you remember, with the applet. I hope you do remember when I was plucking the string in different parts, and the spectra was changing, but the modes were the same. We're going to do the same with the Earth. Now, if you do remember, we considered progressive wave, interference, and we found the modes with the plots. So physics is saying, okay, progressive waves can interfere and generate modes. Mathematics is saying, once you know the modes, you can use them to write progressive waves. And the basic slide to remember for the next is this. Just this. Progressive surface waves will meet. They cross. Can they interfere? Yes, if you put there an integer number of half wavelengths. That's the basic condition that we have used also for the string, if you do remember. It's the same, but on a sphere. That means a mess with algebra. But physics are in this panel here that I prepared here. That's a summary of the seismic waves. So PSVSH, Rayleigh Waves, spheroidal torsional. Travel times, dispersion, and we will see power spectra. And the possible applications here. Body waves we apply to an infinite, beautiful elastic space, free surface, and different layers. Here we need interfaces for interference. Here we need a spherical geometry. These are the bad news. We will start in a relaxed way looking at some animations of progressive waves and maybe one that's it's not easy to see, standing waves.
I'm sorry, I didn't catch the part about tomography, surface wave tomography.
We have no time. I mean, this is a wave physics course. It's not surface wave tomography. What I wanted just to say was the following. But as we have used, the counterpart was this. Where are we? Look. We have not considered into details, but this slide was coming from body waves. Real data, computations of travel times, you try to match them, you do an inversion. Okay? Travel times inversion. Okay. For surface waves, what you can do is the following. Data, you see these dots? These are the measured group velocities of a fundamental mode at two different stations for a single source. Now, you have the tool, the dispersion equation, to produce synthetic curves. And according to this match, you can try to invert for a structure whose dispersion relation is near to these points. So these are the theoretical structures that you can obtain from an inversion of these points here. Travel times, Tx. Dispersion, group velocity, period, or frequency, it's the same. So you're inverting to different things. Are you getting my point? So, really now, we need to pause. Look. There is one slide. Remember, this is a basic course. These principles could be developed later. So here we're just studying the basics. And the basics of an inverse problem is, where is it? Here. For example, here you were measuring travel times. Here you are predicting travel times using a model, and you're trying to minimize the differences. The same scheme, but applied to dispersion curves, could be Vg, group velocity observed, group velocity computed at different periods, and you're going to minimize them. So if you want, again the double nature. Tx, and here you have curves. Remember the ray parameter, right? Travel times at different positions. All plot. Or you can use omega. K. Now, this is not valid anymore, but you have curves. Okay? And what you can do is to measure slopes through velocity at different frequencies. And you start a different inversion process. It's a complementary piece of information. Body waves, times. Surface waves, dispersion. Both they are tools to trying to look inside the Earth. Okay? So, have you received also the final lecture?
Yes.
Okay, we're going to be fast on that one. What I really want you is to remember interference of progressive surface waves can excite the free modes of the Earth. The rest is algebra, that is physics. Okay? So, let's meet again at 11:50 in 8 minutes. Now it's 18:07. It's a little bit in advance.
But for that, to solve the algebra regarding the that you first told, is spherical geometry sufficient? But for log wave, you should have solved by the cylindrical.
Cylindrical geometry would be necessary there. Actually, I was lying to you because now we have solved the plane waves problem, but the real problem in flat geometry would be a cylindrical. But I don't want to bore you. Hankel functions are there. But we're going to jump directly to the spherical one, and Legendre equations are appearing. Okay? But cylindrical, actually in principle, if we are brave enough, we will find here something like that. A source and cylindrical waves that are propagating from a source. But we can imagine to be so far that a cylindrical wave is a plane wave. How it is remembering that it is a cylindrical wave? Because it is a cylindrical wave. So please do remember also that surface waves are cylindrical. Okay? Okay, let's take the bench here. You will be very happy to see this one, right? Yeah, okay. 5 plus minus 1.
Oh my god. Yes. You will take break, but don't kill yourself.
With what?
Take a break.
My break is on my phone.
Oh, okay. Oh, ouch.
Yeah, I'm very tired. I'm going to buy the last time I took coffee.
You what?
The last time I want to take coffee, but I'm scared.
Why happened?
I want to sleep again. I tell you, me. I want you to hold like till the following morning. That sounds fun.
Recaps that day.
Yeah, the last time.
The coffee over here is not nice like that.
It's nice, that's actually nice. My friends are always saying everything. Very busy, very busy. Business, business. I don't know. I don't know. Spend that.
voice is thing.
Yeah. What's the next one?
Yeah.
You should have the one. You should have seen it. You have plans. Bridget.
Yeah.
Yeah. It wasn't anything else. Why are you looking at me? Like, why would you just take it that thing, just take it like that? Why? Well, like say something and it's go with that.
Please sleep. I need coffee.
Okay, coffee will not make you sleep.
Yeah.
It works for you.
It was hello.
Yeah. Because let's go and buy coffee.
I want to be able to sleep. I want to be able to sleep when I want to sleep.
She took 3 cabs that day.
That I want
But I was
to.
really like, there was not really coffee.
There was coffee in it.
There was, well, like, it's not really carbonated. Latte is like milk.
There was coffee.
And
He said
you
you have plans for what?
Like, you have plans. Today. Yesterday's day.
Sunday or weekend.
So, I told you. The next one is here. That's how it is. So, like, you get upset with something and then you wake up
Right
like,
now the laptop nothing minutes. So I'm waiting for Black Friday to buy a laptop.
is that what they told you?
You guys are already planning on getting
Is that
laptop.
what I said? I don't know.
He showed me one yesterday. It was 400 in US.
Elliot.
Yeah.
Why?
He said like media world. He said you don't actually need big space for anything. Just buy laptop with big space, then you end up filling it with movies. And I already have an external like one.
We have an external.
So he said we shouldn't buy HD, we should buy SSD. So even if it's 200 and something SSD, it's okay, we can buy.
You can buy. Okay, me, I have an external. I have a laptop.
And I can even dismantle this, my laptop's 500 gigs and add it to it. So I'm thinking of buying the SSD to 5 something.
What do I have now? I have a laptop, right? I have,
You're asking me?
I have a laptop and I have a 1 terabyte.
Yeah, so you're good to go.
I don't watch movie. I'm not watching movie like in a month. I don't know.
I was
This
moving
I
almost
think.
every day.
So nice.
And yeah, so I'm thinking of getting.
The one that's really old.
Black Friday is going to be cheaper.
No, the one that last Friday. Is that
First Friday in December.
Is it last? Someone was last Friday, no?
No.
But it's supposed to be the global surface.
Yes.
So why?
It's November.
And November, not December.
Yeah. So you get laptop.
Let's see if I can.
You knew what? So like the ones that I like to know will be. Wait. Media.
God, I forgot to switch it off. So the recording is containing a lot of in principle, what we should do, take the wave equation at a global scale. At a global scale, the best approximation is a sphere, okay? And what we should do is to discuss again what we did. Well, we did for body waves, and we realized that if we measure travel times in a spherical geometry, and we use the spherical ray parameter, and so we add an r to the t over dx, okay, we can do that. But for the other waves, what we should do is to take the Laplacian, write it in spherical geometry, here you go, apply the boundary conditions, the free boundary condition, because now the free surface will be at the radius of the Earth. You can imagine that using Cartesian orthogonal coordinates to express that at the radius of the Earth there is a free surface, it would be a mess. So the natural reference system is this one. Good news for boundary condition, bad news for algebra, because the Laplacian now is containing much more components. What we should use, we should separate variables, as we did. And now we have three. Not x, y, z, but radius, colatitude, and longitude. And you can imagine the mess. I will leave most of the slides to your, how to say, imagination. But let's try to understand one thing first, hoping that the web is working. What's going to happen, let's say, in reality or something like that? This is a nice, it should be working, tool to visualize the waves. As progressive waves first, I cannot, if I start, okay. Now we know these ones. P, S, spherical wavefronts, conversions, travel times, body wave arrivals, and later, dispersed, surface waves will appear. You see them here. And at the surface of the Earth, they will be very important. We have seen also an animation. Okay, that's one vision. In principle, we can study that. Progressive waves, right? I hope you agree. It's a matter of bookkeeping. Okay, you can play with this tool here. You have a link in the lecture. Now, what's going to occur at a global scale? That is the same piece of information, but for receivers distributed over the surface of the Earth at until 100 degrees from the source. You see, starting, going. The phases, surface waves. Now, wait a second. Something appears to come back. It's not back in time. But you have to imagine that the waves, surface waves, will travel on the surface, they meet, and then, if the energy is enough, they will start again. So if you're a receiver at the surface of the Earth, you can get many surface wave arrivals. Let's imagine to be here, and the source is here. So surface waves are traveling. The first one will travel on this side. If you consider Rayleigh, it's labeled R1. Then it's continuing. Then there will be this one that will come from this side, R2. Then this one will continue on this side, R3, and so on. As you can see them there. Now, can they interfere? The answer is yes, otherwise we could conclude the course in the previous one. But when? Physically, only when the guitar player was strong enough. Otherwise, R2, R3, R4 are nothing for geometrical spreading and for anelasticity. It would be nothing there. But if the player is strong enough, yes. That's why usually with earthquakes that have a, what we're going to call large magnitude in the seismology course, okay, we can excite the interference between surface waves. And it's going to be a stationary wave, as you can imagine. Like in the string, progressive, standing. Okay? Those are the three modes of the Earth. And this is for the Tohoku event, March 2011. Principle is the same. The player has to be strong, otherwise these other wiggles will be zero. And there is a nice animation that I will try now to stop it. Okay. Now, let me stop this. Okay. Let's give a look to this. This is the recording of what is called the US array. You have to imagine to have a huge network of the receivers over the US continent. Okay? Not continent, but US region. Let's give a look to it. And let me try to go back. Look at the arrival here. It's coming from Sumatra. You will see first phases, then a huge surface wave. Look at the red and blues. And I will leave it now. You see progression. And amplitudes. You see red and blue. Okay? What about this? The other one? Oh, God. Terrible. Now I have to stop this. I have to stop this. And I want to put this here. Look at this one. It will begin to arrive from the other side. Because it's one and then the other. Progressive on the other side. Okay? Let's give a look to this. That was Rayleigh, this is love. You will see progression. Why? Because the wavefronts will be progressive along some directions. In that direction. You see progression, and here you will see progression on the other side. Okay? Now, after many seconds after the earthquake, look here, you see noise. Look at this waveform, it seems noisy. Actually, in that waveform, with a much tinier amplitude, there is a sort of a free vibration. And you will see the difference because red and blue will be different. Red, blue, red, blue, red, blue. It's not a progressive, it's standing. Amplitude here is much smaller, and it seems to be in the background. Actually, if you do the Fourier analysis of this one, you will get a frequency peak, like for the harmonics of a string. Now, what you have to remember, please, is that progressive surface waves can excite the three modes of the Earth. Are we okay with this? Like the string. Now it's coming the boring part. There is also a nice animation here. Let me show it to you. You can Google it. And it's nice. We're rotating. Here it is. We will not see it very well, but that's the Tohoku event, seen on the surface of the Earth. Let me move this. Okay. time. You see progression on the surface. Surface waves now are leaving. If you make the time pass, they will propagate on the sphere. Now the sphere is finite. Our x coordinate is no more infinite. It's finite. And so they can propagate, the wave trains are going to be dispersed, whatever, and on the other side of the Earth, they will try to concentrate and then to start over. Maybe with tinier amplitude, because remember that spreading is playing its role. So it's getting smaller and smaller. But they can cross and interfere. That's the physics. Okay? And this is what you have to know about the three modes of the Earth. The bad news. What should we do? Well, we have to use a spherical reference, R zeta field. If some of you studied the hydrogen atom, it's the same. Yes, at a totally different scale. But definitely we have to use spherical geometry. Three components of motion. Now, question, and please make me happy. Can you map these three into our old flat components of displacement? Okay, you are, for example. You are.
You are.
Not you are, but you are. Sorry for my English.
R cos theta, sine phi.
No, wait, my question maybe is simpler. Now we have a triplet of components there. Can you tell me you are what is in our flat reference system? That would be UZ.
UZ,
UZ.
What about zeta?
UX.
Well, the polar or the colatitudinal component, if you put the source there, it's the direction of propagation. U zeta is x. But for us was infinite. Now it's not. What about U phi? That was y. So if you take a small slice of the Earth, here, and you open it, you're going back to what I deleted, but it would be x, z, and y. Right? So our old log waves are living in the phi direction. Our old Rayleigh waves are in the zeta r. At that time for us, zeta was infinite. Now it's not. It's going to the center of the Earth. But if we imagine to drill a hole and to open it, then the small portion of the sphere will become something like that. Do you agree with me? Okay. These are the good news. The bad news. Wave equation that's valid for every reference system should be solved with this Laplacian. And what we should do is to separate the variables. Any guess? Now, what's going to happen in two components is easy. Very easy. For example, what about time? Well, time has always the second derivative. The differential equation that will be responsible for time, it's always the same. And it is the equation that we found at the beginning of the course, when we consider the harmonic oscillator. Second derivative, oops, battery is going to be over. A positive constant and function. Well, we know it. Since the first lecture, we know that the solution of this equation is the harmonic oscillation. We have found it every time. Second, the phi. Now, what about the phi? Well, let's imagine that propagation is occurring along theta. What about phi? Well, phi is fine because it will be a circle that is going to be larger, then smaller, larger, and smaller. It will be always a circle. So actually, there, we're going to get the same equation. But the dependency is in phi. And if you separate the variables, you're going to find this equation that is exactly that one. What is important is that along a circle here, we have an integer number of cosine and sine. We cannot break it. There is no discontinuity in some point of the Earth over that. It's the phase that is going over. That's why m will be always an integer number. Okay. It cannot be so easy. Actually, this is what we can get for zeta. Now, wait a second. You do remember our old solution in the flat world. For example, for surface waves, we were letting something to be in z, but then we always have considered horizontal propagation, right? Rayleigh waves, okay, they can do whatever in z, but in x they're propagating with phase velocity, for example. So our solution for x was this one, a progression, right? And it was an exponential. Now, maybe you can trust me, but if you want, you can prove it. It's going to take 1 month, if you want. That inside this terrible equation here, that is a form of Legendre differential equation, it's a second order. You can trust 1, 2. There are 2 independent solutions that are terrible. We're going to take a shortcut. And together with this, there will be nothing else than spherical harmonics. Okay? And that can be used to map whatever on a surface that is a sphere. Well, this, in some limit, for very high frequencies, this is giving out exactly this. Remember that e to ik is the solution of the typical equation that we have always found. Well, you can demonstrate that this terrible equation here at very high frequencies or very small wavelengths. What does it mean, small wavelength? Well, when the wavelength is so small that it's not feeling the sphericity of the Earth. Of course, if you take this, you cannot be a liar here. Why it's a sphere. But if you're very tiny, you don't feel it. Actually, the high frequency limit of this equation is this. I hope no mathematician is in this one. But you can demonstrate it. Okay, then once you solve this, and these are the spherical harmonics, you're left with the R dependency. Now, wait a second. R is our Z.
Yeah.
Actually, this equation here, if you perform a wise separation of variables, PSV and SH, is containing Love and Rayleigh dispersion equation. So the only mess actually is here. And that's algebra. But the physics are what I terribly discussed here with you now. So if you want this expression here, that is a vector, because it could be x and z, p and sv, and y, sh, is contained there, but in spherical geometry. What to do next? Well, the first is to give a look to spherical harmonics, and they are a little bit nice. But they are boring. What's happening? Oh, and all this equation, when you separate variables, are coupled, of course. And you have many names now. Because we have, do you remember the string? Yes, you do. You have to know the string to pass the exam. Okay? It's not sufficient, but it's half of the exam. Now, how many quantum numbers do the string has?
You want.
1, because it's a 1D animal. N, the number of nodes inside. No nodes, 1, 2, 3, 4, whatever. Now we are in 3 dimensions. We will need 3. The old N actually is inside this function, because now Love and Rayleigh can be count the zeros along Z. That plot there. Our N is here. The other 2 quantum numbers will be needed to count how many zeros there are on longitude. Good, that's M. And if you want how many zeros there are on Y, then now is theta, that is L. And they are called, there are many names, but sometimes they are called polar and azimuthal numbers. Together, they decide which spherical harmonic you are studying. So actually, the complexity is only in the sphere, in the sense that we studied the flat world, where x, and we were not caring about y, was infinite. Now x is finite, and y is finite. And it's a sphere, okay? It's the news. It's fair. And there are coupled. So M and L will be necessary to describe what's happening on a sphere. The last one, and it is there with K, and that is K, with number, is coupling with time. The blue part is the old part. The other 2 parts are necessary to bookkeep the vibration of the sphere. Okay. Some slides coming from your textbook. But let me tell you, I'm not interested to algebra. I want you to understand what's going on there. And it is in the previous slide, not in this one. But if we want to give a very quick look to, let's say, the solution of these differential equations, we have to remember what is a Legendre polynomial, that usually is defined in an interval. In our case, the interval will be an angle between 0 and pi. What does it mean? On the other side of the Earth. Like the angular distance for travel times. And if we map that, we can find that the second differential equation, the terrible one, can be written and solved using the Legendre polynomials. And there you go. If you want to be sophisticated, the solution of that equation is given by this one. Beautiful, isn't it?
Yes.
Well, you see L and M here, the 2 quantum numbers to describe what's occurring along longitude, M, and in longitude. Longitude and latitude, colatitude. Nothing more, nothing less. Now, wait a second. And this, we're going to spend 1 minute about something that is terrible. That equation is of a second order. So a complete set of solutions should be made by 2 family of equations. Cosine sines, good old times. Enkel, the Bessel function of the first and second kind. Here we have just one. What about the other one? The other one is not appearing here. It's called QLM. It's called the associated Legendre function of the second kind. It's not applicable. Why? Because it has a singularity at the pole. This has not. Good. So it's not physical. It's mathematical, but it's not physical. We can exclude it from our studies because it's not physical. But you have to know one thing. Here, and I think it's It's not written in maybe most of the textbooks. L is an integer. Let me clean this plot. Let me try to do it again. Now we have a source. Waves are propagating here in time. Okay? Now let's follow this line. That's theta. Right? Let's follow this line. That's phi. Now you do understand that for the wave, that's okay. That for the wavefront to be physical, along the line in phi, there should be a continuity. They are the points of the same phase. It's the progression, right? So they know from the beginning that here m has to be an integer. Okay? This line has to be a continuous circle. Now, what about this direction here? In the good old times, it was E2 minus I kx. It's progression. And a wave that is traveling on a string, and you're walking, if it is infinite, you don't have to be an integer. There is no boundary condition until you see the end. Then you have to be reflected to go down and bounce, right? And at that time, we separated progression and become standing on the string. Please remember that the standing string has this. You have to know this to pass the exam. Why? That's the exam. So separation of variables becomes physical and not mathematical when we know the length of a string. Okay? Then we get the quantum number. If you have doubts about this, you have to tell me now. Because we did that. Progression, reflection, 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 standing. To become physically a standing wave, you need to know the dimension of your system. Otherwise, there is no reason to quantize this one, if it is infinite. Let's shake a string that it is infinite. You will travel. You will never become a standing wave. You do understand this? If we know that there are boundary conditions, then we know that we can interfere and be like that. Now, when the wave is progressive, why it should be an integer number here? What I'm trying to tell you is that you become an integer also along the colatitude when you feel that the Earth is finite. Like when you go on the string. Oh, there is an end of the world here. Let's go back. Just to tell you that usually the 3 modes of the Earth are described with PLM with integer numbers. And actually, the menu of the 3 modes of the Earth is changing those two numbers. If you want to describe a progressive wave, you could do that. And it is there. If you sum PLM plus QLM there, you can demonstrate it. It's going to take 2 months. You're going to get this. Okay, I know this was a messy parenthesis, but it was trying to open your minds. Because usually in the treatment there is just P with integer L and M. Remember that for L to be integer, we need interference. Okay. Now, if you want to fully normalize it, here you have the spherical harmonics. Whatever is your spherical problem, you're going to get this. Also for the atom. Hydrogen atom has to be studied with Bose. If you want to write something in spherical harmonics for the universe, you have to use Bose ones. For our poor Earth, we have to use Bose ones. It's algebra, but physics of vibration is here if you want. That's algebra. You can give some names to these parts of vibrating Earth. Oh, by the way, spherical harmonics are used to write the gravity and magnetic potential of the Earth. So every problem in spherical geometry, also a static one, is using spherical harmonics. Our problem is dynamical. It's vibration, seismic vibration. By the way, we can use some names and some conventions. Let's give a look to this one. M is equal 0. Oh, what does it mean? That along the surface, in longitude, we have no zeros. It's just shaking as a whole. But here we have 3. What does it mean? That along theta, we have 3 nodal lines. 1, 2, 3. It's only a matter of bookkeeping. I'm sorry for you. Okay. When you put these slices, you call them zones. The zones, it's written here. The other extreme is this. You have no lines. That's tricky, I don't want to enter into this deep. You see that the Earth now is in slices along with zeros along longitude. Those are called sectors. When you have a mixed number, like in this case here, those are called tessera zones, just names. Now let's consider some simple examples. Look at the first, 0, 2. No zeros along this direction, 2 along this direction. And by convention, you can plot them like this. 3, 3. By convention, when L minus M is 0, you have no zeros along theta. It's a convention coming from algebra. And you have beautiful slices like this. Do you want to mix them? Okay. Let's try to be funny. It's not easy to be funny in this part here. But as I told you, once you solve the sphere problem with spherical harmonics, you're left with the R dependency. Now it would be time to separate variables, x, z, and y. Now it's much more complicated. But what you would get at the end would be what they are called torsional modes, and on the other side, spheroidal modes. In synthesis, Love and Rayleigh. On the left side, the torsional. They are like love waves, pure shear. Actually, it's nothing else than SH vibrations in the spherical Earth. On the other side, you have change of volume. PSB. Rayleigh. But everything is much, much more complicated. But there is one thing that is important. When you go to solve also the radial dependency, you get the third quantum number, the number of nodes inside the Earth. Okay? That modal number is our old modal number for the zeros of Love and Rayleigh waves. And the other two are taking care of vibration on a spherical surface. Now please, tell me one thing. From body wave tomography, we know that we have a core mental boundary.
Yes.
Thanks to Gutenberg and Oldham, and later to Lemon. What does it mean? That the SH vibrations have to stop at the core mental boundary. It's a free surface. So actually, for the torsional vibrations, the Earth is a sphere with a beautiful hole inside. Now you can imagine. Okay. Let's take a hole and open the Earth. That would become a plate. Right? Free surface, free surface. And we studied it. And we found the vibration of the SH vibration in a plate. You do remember that? Okay, please remember that, because after some terrible passages, and this is what I want to save, and that's the second picture of everything, what we get is this. Oh my goodness. It's nice, isn't it? It's a nice plot. Well, that plot contains all the cores that we're finishing. All of it. Okay. I want you to give a look to this one, because in a simpler fashion, you have already seen it. What is it? This. Give a look to this. Now, and let me try to increase. Take this. It's very similar. Well, on the left we have the real Earth. On the right we have a very simple plot of a silly model. Now, okay. Let me go now to the normal vision. I'm showing this to you because it's really the message to take over. Okay, let's give a look to the axis. Here we have frequency. Do you like it? It's in hertz. Yeah, we know since the first lecture that frequency is one over period with 2 pi. It could be the angular velocity, angular pulsation, whatever. It's in a hertz. Let's give a look to numbers. Oh, they are very, 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 very small. That's 1,000 seconds. It's a long period. And here it's, let's say, 0.1. It's 10 seconds. So, in this plot here, we have vibrations that whose the fastest is taking 10 seconds to vibrate. While here we have 1,000 seconds. 1,000 seconds is pretty much 1 hour. So can you imagine a vibration that is taking 1 hour to make a cycle? Could you feel it? No, you can't feel it, but a pendulum that is very long, like 100 meters in the giant cave, a few kilometers from here, it can feel it. And if you take the Fourier spectrum of that one, and if you have a vibration of that, you will have a peak there. We cannot feel it. It's too long. Okay? 1,000 seconds, 1 hour to make a cycle. It's like to give a look to a pendulum that is taking 1 hour to make this. We would sleep immediately. Okay, and that's the y-axis. Is it omega? Yes. Now, wait a second. I told you, this plot is similar to the other one, but the other one was having k. What do we have here? Oh, that's L. L is a quantum number. It's the number that is related to zeta, right? But I told you, if you imagine to be a progressive wave, zeta is the direction of propagation. It's kx. So what was kx in the flat geometry with propagation? Now it's something related to zeta, as we can imagine. What is the link between k, the wave number in flat geometry, and L? And to get this message home, now we need to get this message. No, this one, this. So, actually, if you want to save one slide from this last lecture, please save this one. And you're getting two birds with one stone, because if you have to study atomic orbitals in a spherical geometry, you would do exactly the same plot. Because this plot is simply telling us what are the geometrical conditions for interference on a sphere of 1 micrometer or with a ray of 6,371 kilometers. What do we do here? What should we do here? Okay, let's imagine to be two progressive waves. Okay? We're going, okay? If we want to interfere on a sphere, we cannot be like that. We should go together, right? It's a boundary condition. And if you want to write this condition of interference on the theta coordinate, what you have to do is that in this circumference, 2 pi times r, there should be an integer number of half wiggles. Now, you do want to pass the exam, right? Good to know. And I told you, do you want to pass it? Please remember, take a string, plot it, and then start doing silly things. 1. How many half wavelengths there are? 1. 2, 3, 4, 5, 6. Put it whatever until you go to the solid state physics course. Right? Okay. The same trick is here. But now the string is 2 pi times r length. Okay. Now, that condition is giving something like that. You see, if you want to pass the exam, you have to make this plot. If you want to be a little bit more sophisticated, right? Right? Okay? And you're getting immediately that one. Okay? You're getting immediately that one. Okay. Now we have to do exactly the same. Because lambda is nothing else than okay? 2 pi a has to contain an integer numbers of half wavelengths. Okay, good to know. Now that's just a very simple geometrical condition. Now please compare this with this. What is K here, really? K is L. Look, you should say, wait a second, L is a number. Is not a wave number. Yes. What are the dimensions of the wave number? You have 1 second to answer. Over meter. Okay? Look, A over A is 1 over meter. Many meters. But physically, is L that is representing K on a sphere. If you want to be accurate, it should be L over A. Okay? Now, I hope you do. Okay. And now, if you want to find an analogous using this and this, you will get what is a phase velocity on a sphere. That's the expression that you have to remember every time. High school physics. So high school physics here, and here just geometry. Now, if you solve the problem, and you make the plot of frequency, omega, and L, that is representing K, now you're getting this. That's the picture of the Earth as seen by torsional modes. Let's give a look to it. Okay, L is K, right? Is representing K. It's not K, but it is representing K. What does it mean? High numbers of L. High numbers of K. Right? What is high number of K? Small wavelengths. Now, small in terms of what? In this plot here. Remember that we have A, the radius of the Earth. So when the wavelength is small compared to the radius of the Earth, here you don't feel the sphere. And when the frequency is getting larger, actually you're living in the flat Earth. That's why here the torsional modes are becoming love. Love waves, not love, but love. So what we studied in the previous lecture is here. Now let's go the other trip. Let's get down with L, and that means, okay, let's go to large wavelengths and small frequencies. Now forget about this inset here. Would you say that these are lines or dots?
Lines.
Oh, to me it seems a line.
It's a line.
Seems a line. It's not.
They must be correlated.
Actually, it's made by a very dense set of dots. So dense that we cannot distinguish them. But if we go here, there, what you see is this. So if you use a lens at very large wavelengths, very low frequencies, very long periods, and you give a look there, because actually this is this, you see the discreteness nature of the modes. And you see here, that's 2, T02. It's the torsional mode with no 0 inside the Earth, with just 1 there. It's the lowest possible mode for torsional waves. Now you have to know, I was shortcutting this part. There are some rules here that could be understood just using algebra. But this one is the lowest mode of the Earth. It's about 40 and something minutes, torsional. And if you want to see it, it's here. I hope that I have dated this. Where is it? Okay. It's nice, isn't it? It's like that. It has no nodes inside. Here the representation of the Earth is not accurate because torsional should have a hole there. But it's the core mental boundary. But it's the best animation that I've found. But you see, it's something like that. Now, if you go locally here, there, it's nothing else than an SH wave. It's the fundamental love mode. Of course, you can increase now the number. And you can add zeros inside. And you get very complicated vibrations. You can increase them, and then you can get sick. Now you can increase the number of vibrations, increase the complexity. But the main message here is that here we have love waves, the ones that we have just studied. When you go to very long periods, very large wavelengths, then you feel the discreteness of the modes of the Earth. But if you move out, or you go to very large order numbers, large Ks, and high frequencies, those dots are so dense that they are lines, and we're going back to the flat world. Now you should ask, what about Rayleigh? Yes, you're right. We should do that. Everything is double, triple in this case, trust me, and that's division. So you can do that. Now, let's stay on this picture for a while, because it's really containing everything. Here you have surface waves. Here we have the modes. Here, what do you have? Well, if you sum properly the modes, and in the omega k plane, remember that slopes are velocities, you can write also this wave here. What is this? It's the S body wave diffracted inside the Earth by the core. And it is made of many pieces of different modes. Because if you know the modes of the Earth, you can write whatever on the Earth. So body waves, surface waves, the modes of the Earth. What we have been shortcutting, let me show it quickly to you, but I don't want to. Really, the picture to take home is this. It's easy. You agree with me? Is it fine? It's like the string, but on the theta direction. So the integer number in theta direction is representing the k that was progressive there. And if you go to this vision here, you see those dots, the numbers, as continuous lines k. And in the Earth, the modes are a complete orthonormal system of eigenvalues and eigenfunctions. Do you want to see the eigenfunctions? Just a very quick look with different labels. This number here is the love wave mode. Remember that torsional are stopping at the core mental boundary. P or not. That's why the spheroidal modes can go down to the center of the Earth. The bad news is that they have two components. But let me amuse you. In the spherical Earth, if you want to be accurate, Rayleigh waves have three components. They have a huge x and z, theta and r, but they have a tiny phi one. Do you know what? The torsional, they should be just like that. They have a tiny theta component. But let's forget about that. Okay? Let's say that love, torsional, Rayleigh spheroidal. And let me conclude this part with this. That's the map. That's the most important one. If you want to label the fundamental and lower order number modes of the Earth, you can do that. You have to know that the theory was developed before Lamb, Love. And they were not that wrong. What you have to remember is that the lowest torsional mode is this one, T02. Why T01 is not there? Because T01 would correspond to the total rotation of the Earth. There is a convention. The number of zeros along zeta for torsional has to be L minus 1. Now, can you imagine the whole Earth rotating like that? No, conservation of momentum. You cannot have this. I cannot open the door. I need an external source. So in principle, you could excite T01 with an asteroid and make the Earth flipping this way, but not an internal source. So the first excitable mode is this one. You see it's a little bit less, let's say around 40 minutes. What about S? Well, we may have 0, 0. It's briefing. That's allowed. But the longest one is this one, S02. It's called the football mode. Now we're going to see it. It's 54 minutes. Could you imagine to see a pendulum that is taking 1 hour to oscillate? No. But you can measure its values. Let's give a look to, that's 0, 0. That's 0, 2. I think we can use this one. Okay. There you go. You have two nodal lines along theta. Please don't imagine that the Earth is vibrating like that in reality. Amplitude is tiny. So tiny that we cannot perceive it. What we can do is to take those tiny amplitude wiggle time series to perform Fourier analysis and to look for peaks. And that's a typical vision. I think I was removing them. It's in the hidden part. Okay, that's a typical spectroscopy of some modes of the Earth. You label them by frequencies. Now really the final part. I will never ask you, but you have to know it. The first slide of this lecture was this, and you have to know that. A necessary and pretty much sufficient to pass the exam is to remember this. The exam is much easier than this one. But that's the model summation on a string. Okay? Is it a yes? As a chorus? Okay, good. We can replace the same expression in the Earth. It's a mess, I know. But we have to sum over all the modal numbers. N, L, M. And we have to sum for all the components of motion. PSB, SH, spheroidal, torsional. And it's a mess. But if you want to see it, there you go. We could do that. I will not ask you. But look at this structure. Eigenfunctions excited by the source, and the sum over the modes, that's an operator to take care about anelasticity. These are the eigenfrequencies. Let me conclude with this. If you properly sum the modes of the Earth, you can write progressive waves, like SCS. If you write properly, I was hiding the other one. There is another one here. If you properly sum the modes of the Earth, you can write surface waves, of course. They are surface waves. So message to take home. If we take a spherical geometry, we separate the variables, we do all our beautiful but terrible algebra, we can separate the problem into two, PSB, SH, spheroidal torsional, like Rayleigh and Love. Plus, if we properly do this similarity process, we have also the body waves, because now we have a finite body. Remember, in flat geometry, X and Y are infinite. Spectrum is not complete. Here we have. Actually, and with this I want to conclude, and we're in time. We started from the oscillation of a single point with a linear restoring force, harmonic oscillator, one frequency, square root of k over m, long time ago, or a pendulum, length, and gravity. We coupled oscillators, allowing energy to flow in space and time. Later, we discovered two wave equations, sound wave equation and the wave equation for the string. Later, we made a little step backward to understand lattices and looking for phonons, discrete, finding dispersion. Then we considered more complicated systems like solids. We generalized Hooke's law. We created stress and strain. We considered a homogeneous isotropic world. We found lambda and mu. Lambda was similar to bulk modulus. Mu was a new rigidity modulus related to shear. In an infinite homogeneous body, we found two waves. P wave, like sound, but more complicated, and S waves. And if no interface, they will never interfere. Then we added an interface, a free surface. And we found that P can generate SV and P. SV can generate P and SV. Good. SH, nothing. But at each interface, we can do that game with many other phases. We considered for seismic phases the plane Tx, travel times. And we found the concept of rate parameter. And Snell's law is making that parameter to be constant for something that is traveling inside. Body wave tomography. Then we revisited the free surface condition, looking at the Rayleigh idea. Can P and SV travel together with a common velocity? Yes, Rayleigh waves. And in a normal Hall space, no dispersion. Then we added a low velocity layer, but we studied also for travel times. And we found that SH can interfere. Love waves. And we found dispersion, progression and progressive waves. E to ikx. As a final step, we understood that if sufficiently excited, surface waves can cross each other and interfere. Okay? And physically, this would correspond to the excitation of the three modes of the Earth. Rayleigh spheroidal, SH, Love, torsional. More complicated. Formally, mathematically, like in the string problem, we can write the wave equation, separate the variables, take care about boundary condition, but it's a mess. It would take one course, no, 2 courses. I'm not joking, but okay, the principle is that one. Then what you would get is a spectral representation of the Earth with 3 dimensions. Theta was the old X, phi, that is our Y, but now is always a circle, and R, that was our old Z. So, mathematically, we can study the modes of the Earth and use them, like Fourier taught us a long time ago. If you properly sum them, you can write whatever. So instead of listening to music with our MP3 players, digital players, we can write synthetic seismograms using the 3 modes of the Earth. It's a different music. Okay? So from one point that was vibrating to the Earth that is vibrating as a whole. That's the path. I don't care too much about the algebra, except for very simple systems. No mercy on that. But for spherical geometry, that's fine. Please remember the logic and the physics, and your work is done. What we're going to do is to meet, let's say, informally on Thursday. We will try to solve some simple exercises, similar to what we're going to discuss in the 5 exercises during the exam. As a final step for Thursday, I'm going to give to you some the last homework. That is something between the last -1 and just thinking about the boundary conditions of layers that we have discussed on Friday and today again. Just 3 and 1. Just to play with boundary conditions and to plate interference and low velocity layer interference. That will be maybe a part of the exam. Okay? Just thinking about boundary conditions. Do you have all the material? The old one, I'm sorry for the website, it's out of my power, so I cannot. Okay, so let's meet on Thursday at 4, as far as I remember. 4, I don't remember. Every time that I do this, it's a mess. Let me try, okay.